Welcome back to What is 5G and how is it measured correctly? Here in part 4, we want to consider the measurement of the actual maximum exposure. We have already looked at how to measure the actual EMF exposure level. You either make a broadband measurement that captures all services including 5G, or you make a frequency selective measurement that obtains the exposure level for each service separately. So much for the actual or instantaneous exposure level. But what if the question is, how can I be sure that the installed system does not exceed the limit value at any time? The answer then is not so simple. The value that is required now is a maximum possible value, not the instantaneous value. So we first need to find out by just how much the signal level of a mobile network can vary. As you know, this level depends on many factors, such as the load, distance to subscriber, and so on. If you don't know anything about the network, how accurate can the measurement be? Or how much do you need to add to the measured value to be certain that the system will never exceed this? To answer this, let's look at the dynamic ranges of mobile communication systems. By dynamic range, we here mean the difference between the minimum output level of the system, that is, when the system is idle or only transmitting the signaling, and the maximum output level, when all traffic channels are occupied and the subscribers are at the maximum possible distance from the system, so that the base station is transmitting at maximum power. The maximum dynamic range of the output power of a 2G system is not more than 6 to 8 dB. This means that you can make a measurement at practically any time and simply add 6 to 8 dB to the result across the board to extrapolate the result. As long as the extrapolated value remains below the limit value, there is nothing wrong with using this simple approach. There is often enough leeway between the measured value and the limit value to allow this method to be used. The dynamic range for 3G is already 7 to 10 dB. This means that the system is more efficient and reduces its output power more distinctly if there is no traffic. A 20 MHz LTE system can have a dynamic range of more than 10 dB. With this kind of dynamic range, simply adding a value across the board is not enough. Accurate extrapolation is necessary. If you encounter a full load situation and have simply added a further 10 dB, you can very easily exceed the limit value. And 10 dB is a factor of 10 for power. The efficiency of 5G systems is even higher. So to properly analyze the risk, you either need to measure permanently by using an area monitor, for example, or you must extrapolate your measurement result. This is the only way to ensure that the limit value will not be exceeded at any time. So, how do you extrapolate correctly to obtain the actual maximum exposure level? There are already international measurement recommendations, especially for 3G UMTS and 4G LTE network, that have been issued by the ITU and the IEC. A measurement recommendation for 5G new radio is being developed. NADA is involved in this process and has already made concrete proposals for such a measurement. The SRM 3006 can already perform standard compliant extrapolation for 3G and 4G. The UMTS and the LTE TDD FDD options can demodulate the signals and carry out an extrapolation that complies with the standard for the information obtained. But why is there no 5G demodulation for the SRM 3006? If we were only considering 5G, then the matter would already be settled. NADA has already made preliminary investigation to see if the SRM 3006 could demodulate 5G, and the signs here are positive. But we are not just talking about 5G here. There is also beamforming to consider. Beamforming will go hand in hand with 5G, and to ignore this would be foolish. The principle of extrapolation is based on measuring parts of the signaling signal and then calculate from this what the level would be at maximum traffic load. So far, this has worked fine, and when it comes to accessing base station, this has essentially become the standard for this. But it doesn't work when beamforming comes into play. Beamforming means that it is possible for the antenna gain for the signaling to be different to that for the traffic. So if you want to extrapolate from the signaling to the traffic, you must also take the difference in antenna gain between the two operating states into account. Otherwise, it would be like measuring apples and calculating pears. The difference in antenna gain is not a fixed factor of xdB. This difference can show very great spatial variation. For example, if the signaling is transmitting without beamforming and the traffic with beamforming, the beamformed signal can cover a much wider area than the 120 degree. And the beam can also be depressed further in the tilt range than it is possible for transmitting without beamforming. As a result, a difference of several tenths of decibel can occur, particularly at the edges of cells. In addition, this difference in antenna gain is such as it results in an underassessment. This is, of course, totally unacceptable from the point of view of safety. And these considerations also apply to 4G when beamforming is used, not only to 5G. So beamforming is a real challenge for the measurement technology. As we have mentioned, NADA has already proposed two measurement methods for 5G, the most recent being published in Health Physics. But both these 5G measurement methods assume a fixed or known factor for the difference in antenna gain between signaling and traffic. Our current view is that it is no longer realistic. Right now, NADA is in discussion on the development of a new measurement procedure for 5G beamforming with various national and international bodies such as IEC. Nearly all the manufacturers and service providers are involved. The proposal made by one manufacturer is currently being investigated. As you can see, everyone involved is keen to find a solution. Even the most sensible limit value is useless if it cannot be checked. So far, August 2019, we have not found the answer. Let's summarize. 5G and beamforming are fascinating technologies. When it comes to safety in the field that they generate, NADA can already offer a wide range of 5G capable devices, starting with personal monitors like the Redman 2 and the NADALert S3. You are also in safe hands using our NBM products for measuring the actual radiation level in order to protect the general public, and our area monitors for long-term monitoring. And the SRM 3006 is still far and away the reference device that is currently being used for nearly all the investigation into the development of a measurement procedure for extrapolation. The expansion of its frequency range to include the second stage of 5G network development is already on our roadmap. At the same time, we continue to work with all concerned on the development of a suitable measurement method for the extrapolation to the actual maximum exposure level. To keep up with the latest, subscribe to our YouTube channel or to our news ticker on our homepage. We are always on the ball to ensure 5G safety.